Hello guys, welcome back to another video in Consultant Explains Maths. Today I want to talk about another exam question that I had when I was a graduate student this time. But don't worry, I don't think it's actually a difficult question. It was just that I ran out of time because I didn't really know what I need to do. So here we have the question here. The statement is actually quite simple. We have A to B this 4x4 matrix with a pattern, in fact, in the entries of the matrix. So in the diagonal, we have A1 in the elements right next to A1, we have A2. And then on the left, on the rightmost, because we don't have an element on the right of A1 in the fourth row, we move it to the leftmost column of the fourth row, and so on and so forth. And also we have this matrix, which is, if you take a look at it closely, it resembles an identity matrix with the number 1 being shifted 1 column to the right. And as always, because we don't have another column at the end of the fourth row, we move it to the leftmost column. Now we are told to find the eigenvalue of A. You can do it the old-fashioned way by solving for the characteristic polynomial of A, that is to find the roots of this particular equation. But it doesn't really take long for you to realize that if you were to try to do this the old-fashioned way, it's going to take very long as you try to solve for, well, this. And really, I don't even need to write down the entire matrix for you. You get the idea. It will take very long. But what if I tell you that the eigenvalues of A are the following? So if we have I'm going to tell you that there are 4 eigenvalues. Just bear with me. So I denote the eigenvalue as lambda. So we have A1 plus A2 plus A3 plus A4. The second eigenvalue is A1 minus A2 plus A3 plus minus A4. The third is A1 plus A2 times I, where I is the imaginary number. And the fourth one is this. Wow, very quick. How did you solve it in just a mere matter of seconds? Well, okay, obviously, I've practiced before this video, otherwise I wouldn't be able to solve it in just a few seconds. But really, the pattern of the matrix is what allows me and would allow you to later solve for the eigenvalues of A in a very quick manner. So how do we arrive at this in a very short amount of time? Well, this time I don't really want to talk about the exam question itself. The exam question only tells us to find the eigenvalues of A for a 4x4 matrix of this kind, but because of the pattern here, you would expect this to be generalizable into bigger matrices with more dimensions, with more columns and rows. Okay. So first of all, I need to introduce you to the matrix we have at hand here. So we have A to be similar to the above matrix. So A1, A2, A3. Let A be an n by n matrix, so we have an n columns here. And then we construct the next rows by shifting the top row here by one column to the right, if that makes any sense. Basically, we move each of the elements here one spot to the right, so that we have the second row as A1 on the second column, A2 on the third column, all the way to AN minus 1. And then here, because AN has nothing to, because AN doesn't have any space to go, it goes to the leftmost column. So AN is here. The third column is obtained by moving the elements on the second row this time, one column to the second row to the one column to the right, A1, and then here this is AN minus 2, AN minus 1, AN. And then you continue doing this, the other entries, such that you obtain, this is to be A1, this is A A2, A3, A4. Right. Now, how can we find the eigenvalues of this particular kind of matrix? Actually, let's not jump into the question first. I'd like to introduce you to this new friend of ours. So this matrix with its easy to remember pattern actually has a name. This is called the circulant matrix of size n times n. And this is related to another matrix that is similar to the one we have as C. That is, picture the identity matrix like this, and then shift each of these elements one column as per usual. So you would have 0, 1, 0, 0, 1 here, and then okay. And then 1 is supposed to be here, but we're not gonna write it down. And then here, and then 1 is here. There's supposed to be a 1 on top of this last 0 here, but okay. So how is it related to A? Well, notice that if we were to take only the elements, take only the A1, as in if we were to write down A but only leave out A1, while the others are omitted and be equal to 0, you'll have A to be equal to A1, A1 here, A1 like this, everything is 0. And then you can add a matrix full of A2s, in which the A2s are arranged in a way that you simply put in the elements, you simply put in the entries. Basically, if A2 is here, then it must occupy the same entry in this matrix, if that makes any sense. There's A2 here, A2, 0, 0, and so on and so forth, basically. You can continue with A3, A4, and all the way to AN, but it doesn't really take much to realize that there seems to be a pattern here. So you can write down A as A1 times the identity matrix, as you can see. And now here the A2 is just A. And then here the second matrix can be written as A2 times C. And you might be wondering, what about A3, A4, and so forth, so on and so forth? Well, want to take a look at what multiplying C by itself multiple times does to the values of matrix. So we're just going to do one multiplication, and then I hope you'll be able to see the pattern. It might not be easy to picture this with a variable size matrix. So I'm just going to show with 4 columns and rows instead. I figured it out. Okay. It's not hard to see what multiplying C by itself does. It basically shifts the ones here in the C one column over to the right. So it's 0, 0, 1, 0 here, here, and here. What about C to the power of 3, say? Well, if you were to multiply C to the power, if you were to multiply C by itself 3 times, you can also see that what our matrix C does when being multiplied by itself, when being multiplied, is simply permute the matrix that we have. And that is basically a qualitative description of what we're doing with what we're doing when multiplying C by itself. Really, any matrix by C, you're basically moving the rows and columns around, and there's a reason for that, because this is an example of a permutation matrix. We're not going to go too deep into it, but permutation matrices, when multiplied to another matrix, can be instead of basically permuting either the rows or columns of such matrix. But it's also not hard to see that here, in this case, e to the power of 3 is simply, oops, this. And you can picture what happens when you have an n by n matrix multiplied by itself, n by n matrix that is like C, multiplied by itself multiple times. You're simply shifting over the ones. You're simply shifting over each of the rows multiple times. And because of that, we can see that A can be written as a linear combination of I and the powers of C. Or maybe you can say the powers of C, like this is C to the power of 0, right? So this is A3 times C to the power of 2, A4 C to the power of 3, all the way to AN times C to the power of n minus 1. Or in summation form, this is this. Okay, now that we get this established, you might be wondering, how are we going to find the eigenvalues of A given this information? Okay, so now let's rewrite that. A is equal to okay. To find the eigenvalues of A, you have to recall what being an eigenvalue does or means. So we know that if lambda is an eigenvalue and v is an eigenfactor of A, then it must satisfy this relation. The problem is how would we quickly find v and lambda? Well, it turns out you don't actually need to find v. We just need to find lambda. Or maybe not really lambda. Let's just give a different layout to that. Maybe let's call it L, for instance. So now we have to take a look at the summation form of A to look for ideas where to start. The idea here is basically, what if we were to multiply both sides by an eigenvector of C? Now we let, for instance, W to be an eigenvector of C. We don't need to know what the actual entries of the eigenvalues of C are, but that will help. What if we multiply both sides by W? And because W is an eigenvector of C, it satisfies the relation C W equals lambda W. So here we go. AW equals, you can expand this summation to make it even clearer. AK times I times W. Oh wait, hold on, this is not AK, this is A1, A2, CW plus A3, C R of 2 times W, all the way to A times, oh sorry, AN and C to the power of N minus 1 W. Now, we have to evaluate each of the terms one by one. So it's A1W plus A2 lambda W plus A3. Remember that when we have this, if we have the higher power of C, we can simply multiply both sides by C. So it's C squared omega is equal to C lambda omega. C, not omega, sorry, that's W. And remember that CW is equal to lambda W, so this is lambda squared W. So really it's lambda squared W all the way to alpha to AN lambda N to the power lambda to the power of N minus 1 W. If we factor out the W, if we factor out the W, we will obtain A1 plus A2 lambda plus A3 lambda squared all the way to AN lambda to the power of N minus 1 times vector W. And there you have it. Because this relation holds, then this has to be an eigenvalue of A. We're saying A because we know that omega is an eigenvector of C, and being a full rank matrix, or where's C? Being a full rank matrix, it would have n eigenvalues and eigenvectors as well. So our task reduces to finding the eigenvalues of C, which we still need to do manually, but it will not be as difficult. Okay. Okay, let's pause this solved for a while. So what about the eigenvalues of C themselves? Now recall that C is, okay, I'm not going to rewrite that. But actually, here we can use the old-fashioned way of finding the eigenvalues of C. That is by solving for the roots of the characteristic polynomial. So you will have lambda minus 1, 0, 0, lambda minus 1, lambda, there's minus 1 here. There's a -1. And yeah. To find the determinant of this matrix, we need to use the minor factor rule. And it does depend on the number of columns and rows that we have. But the final result will be the same. And it's up to, and I'm going to leave this to the viewers as an exercise to verify that both the even and odd values, both the expression for the characteristic polynomial are the same for odd and even numbers of columns and rows. So this time we're going to take a look at the expression if we have an even number of columns. So okay, this might be a bit awkward here because I have to move backwards and down. Okay. So when n is even, we assign a plus here, negative here, plus here, all the way to the last row with a negative. Now I'm just gonna let the viewers verify that this results in lambda times determinant of -1. Was it -1? Oh, sorry, no, it's not 1. That's lambda, sorry. That's another lambda. -1, 0. Here's a lambda. Here's another. And yes, this matrix is going to be mostly similar to the previous one. And then we have a negative. We have a negative times, negative 1, which can be combined to +1 times -1, 0, 0, 0 lambda -1. So, yep. Okay, from this step, it's not hard to see that if you were to do the minor factor rule multiple times, you'll see that this matrix will be basically reduced to just lambda times lambda, and then when you apply another one, it's going to be another times lambda, and so on and so forth. And so the determinant of this matrix here is basically lambda to the power of -1. So in full, this is n lambdas. And then we have +1 times -1. Hold on, I think I made a mistake here. Did I? No, I didn't. Okay, you just go along this direction multiple times. And then you will obtain -1 times -1 to the power of n. So we have lambda to the power of n -1 because n is even. So sorry, yeah, n is even. Wait, was n even? Oh, sorry, n is odd now because we have reduced one of the we have taken out one of the columns. I forgot about that in the previous step. So because n is even, then n minus 1 is odd, and therefore -1 to the power of n minus 1 is -1. So here we have the characteristic polynomial, and we have to solve for this. We have to solve for the roots of this polynomial. Now, if you remember your complex analysis, you will realize that we are looking for the nth root of unity in this case. So basically, the solutions of this are of the form e to the power of 2 pi I n. But remember that it's only one of the solutions. You can plug this in, so you will obtain e to the power of 2 pi I n times n is equal to, well, e to the power of 2 pi I, and then by Euler's formula, we have cos 2 pi plus I sine 2 pi, which is equal to 1. But remember, there's only one of the solutions. We can actually plug in, for instance, e to the power of 2 pi I times 2 n. And then it will still result in the same thing, because if you plug it in, you will obtain e to the power of 4 pi I, and this is also 1, and so on and so forth. If you were to list all the angles that would solve this equation, then we would have lambda to be equal to e to the power of 2 pi I times k over n, and sorry, where k is equal to 0, 1, all the way to n minus 1. And it's not hard to see why, and I'm leaving that as an exercise to the viewers. I forgot, I should be also saying that when n is odd, it's also an exercise for the viewers. Okay, let me just expand the space. So there you have it. The eigenvalues of C are precisely the nth roots of unity. That is, lambda is equal to e to the power of 2 pi I k over n. And yeah, okay, I just repeated myself, but you get the idea. You just have to plug in k is equal to 0, 1, all the way to n minus 1 to obtain all the eigenvalues of C. But remember that we are looking for the eigenvalues of A. Now remember the expression that we found out earlier. That is this box. A bit cluttered, I know. Apologies for that. Emphasis. Right. So the eigenvalues of A are nothing but simply A1 plus A2 lambda plus A3 lambda to the power of 2 all the way to A to the power of n lambda to the power of n minus 1. And that is it. You basically plug in each of the eigenvalues of C into this expression and obtain n eigenvalues of A. And this is also how we obtain the formula for a 4x4 matrix. That's the reason why we're able to solve the eigenvalues of A earlier in the video very quickly. Okay. There you have it. So in the case of n equals 4, lambda aren't equal to 1, -1, I, and -I. And so you plug those into the polynomial, into this expression, and obtain the eigenvalues that we just found out earlier. That's about it. So now I really want to take a look at the eigenfactors of C, but I figured out it would make the video way too long. So I'm just going to leave out that process, which shouldn't be too hard to the viewers. Okay, I think that's all I have time for now. Thank you for your attention. Goodbye.